Hello and welcome back. Today is the first day of third week of this lecture series. So, in the previous week we learnt about the fundamental issues involving the laser construction, and we learnt about how we can amplify the stimulated emission to get laser. Toward the end of the class in the previous week, we started talking about the threshold condition. So, we can understand that there are there are two things. One is the amplification of the stimulated emission, which is the gain, and there are several losses that we will talk about today. So, there must be an optimum value of this gain above which we can see laser output, otherwise we will not see so called quote unquote laser output. So, we need to learn about the threshold conditions. Okay. So, we will start from there today. So, we have learned about population inversion already, okay, and we also know about the stimulated emission. So, knowing the population inversion and stimulated emission, what we can say is the intensity of stimulated radiation, stimulated photons, the change in that intensity will be proportional to the difference in the population in the two levels involving the laser action. So, if I write the populations of the upper and lower states as N2 and N1 respectively, and the intensity of the stimulated photons as I, then the change in the intensity I with time, that is the rate of increase of stimulated photon, we can write as di dt, and you can see this is the this is positive. So, it signifies that there is an increase. Okay. In case of a decay, we write it as negative, we know that. So, this is proportional to the population difference. Okay. So, we can write this in a very similar way as we have already learned in the first week of this lecture series, with a rate constant, okay, which is for stimulated emission into the initial intensity, like this. Okay. So, this is for a case where I have considered only two states and having no degeneracy. Degeneracy meaning that there are several such states having the same energy, okay, so and the same properties. So, if I say for the state having population N1 has a degeneracy of G1, that is G1 number of states have the energy of this state, which is, say I write E1, and then correspondingly this is G2. So, it is better to consider these degeneracies, because in real life there are several states having degeneracies. Okay. So, if I consider this degeneracy, then it will be okay. So, up to this we should not have much problem, because we have seen very similar kind of formalism. Okay. So, now we are only thing is that we are talking in terms of the intensities of the photon and the rate of increase of intensity. Now, this is a differential equation, and what will be the solution? So, solution is I equals to I0 at a time t equals to 0 e to the power a t. Okay. So, all right. Now, this is expression of intensity of stimulated photons at any given time t. Now, we know that time is related to distance, and time is related to the speed of light, and we can correlate the time with the distance using the speed of light, okay, because we are dealing with the properties of light only. So, t is equals to x, where x is my distance, whatever that be, okay, by speed of light, correct. So, in real systems, we may encounter a medium which is different from, say, vacuum. Okay. So, in that case my expression will be modified to C prime, where C prime is nothing but taking into account of the refractive index of the medium, right. So, this is my refractive index of the medium. So, fine. So, since I can convert T into this, I can express this equation in terms of this one also. So, one thing I forgot to mention. So, this A is essentially nothing but N2 minus N1 with the degeneracies, maybe okay. Okay. So, now if we express this in terms of the distance x, then how we can write that? We can write as I equals to I0 into e to the power a and x by C prime, right. So, if I club this a by C prime, then I can rewrite this one as like this, where my k is equal to a by C prime, which is this. Okay. So, this is my expression for I for a particular distance that my photon may be traveling. Okay. Now, this k is known as small signal gain coefficient. Okay. So, we will remember this one, that k is a gain coefficient. So, we will utilize this one in a later step. So, in actual condition, okay, so in practical world or in practical situation, we have several losses in the cavity, losses which we have several sources of losses. What are they? So, which comes from the error in the reflectivity. So, reflectivity errors. What does it mean? That I know that one of the mirrors should have 100% reflectivity, another one should be partially transmittive. So, say has 98% reflectivity. But if in in reality, if it is not 98%, if it is say 97.5% and the other one is say 99%, then it is different from what we expect, and in that condition I will have losses. Okay. So, this is one. Second, there are several other things in the medium. Okay. So, suppose I need to cool down my I need to cool down my flash lamp, because that will create a lot of heat, okay, or the electric discharge system. So, there will be liquid media and all. So, there are chances of absorption of photons, and this absorption is not necessarily going to take place within the medium itself, but it will be it can be absorbed in several other parts of the cavity as well. So, the moment there is an absorption of the photon, then we are getting an output which is less than what it should be. Okay. There can be scattering, right. There can be diffraction, there can be non-radiative decays, which means that I want lasing, I want stimulated emission from here to here. So, these two states should be radiatively coupled, but instead of a radiative emission, if there is a non-radiative emission, that is the molecule sitting here relaxes back to this state without emitting photon, that is non-radiative decay. We have learned about that. So, if there are certain amount of non-radiative decay, then also we are actually losing the amount of photon. So, there are several such losses are present within the cavity. So, we need to take care of these losses, then only we can get sufficient amount of laser output, all right. So, all these losses, okay, there are few more losses that we can take into account. So, if we consider a particular type of cavity, so we can figure out what are the different types of losses are there and what are the total amount of losses. And if we club all of them together and put all the loss by this gamma, so gamma refers to total loss within the cavity. Then I need to modify this. Okay. So, how should I modify this one? I should modify this as I0 into e to the power k minus gamma. Why? Because k is my gain coefficient. So, the losses will take out amount from my gain, correct. So, this is what I will get. Okay. So, I equals to this. All right. Now, we need to consider another thing. We got this expression thinking about the active medium, the process involving population inversion and stimulated emission and all the losses. One thing we did not consider, which is by design of a laser cavity, it's always there. What is there? Because I know for a laser cavity R1 is not equal to R2, where R1 and R2 are the reflectivities of two mirrors. So, one is 100%, I will assume 100% here, because I am already taking care of the losses which is known to me. Okay? So, we should not doubly count it, and this R2 say 98%. So, you can see that this is not 100%. We know that, okay, this is by design of the laser. So, this 2% always go out. I need to consider this here also, because that will lead to that overall intensity or the photon density within the cavity, correct. So, this expression has to be modified as I equals to I0 k minus gamma x multiplied by R1 multiplied by R2. This is my real life situation, right. So, if I now rewrite this one as I by I0 equals to R1 R2 into exponential k minus gamma x. This term I by I0 is known as gain, where G is my gain. Okay. We have been talking about gain and all. So, this is the mathematical form of the gain. So, if we really need to have laser amplification, so for laser action, that means a true amplification, right. So, true amplification. What we need? We need this quantity to be greater than 1. Okay. So, when gain is greater than 1, that is more than 100%. So, I need G to be greater than 1. If G is not greater than 1, so if say G is less than 1, what do I have? I do not have any amplification. So, essentially my the photons which is coming out of my device, okay, if I call it laser or whatever, when G is less than 1, the photon characteristics are very similar to the spontaneous photon. Okay. So, at this condition, the characteristics is very similar to spontaneous emission. So, the device will work just like it will work like a conventional light source. We do not have any problem in understanding this one. So, if there is no amplification, so basically it will be spontaneous emission which is dominant, and it will be just like a chaotic system. Okay. What is chaotic system? We will talk in a while. So, we definitely want this G value to be greater than 1. So, that means there is a threshold. Okay. We started saying that there must be a threshold, okay, and this is how it looks mathematically. Okay. So, how do I know what is the threshold condition? So, how to find out? Find the threshold condition. It is very easy, right? It has to be greater than 1. So, if I find out what is the condition on, say, this gain coefficient k when g is equal to 1, that means if I just increase, go above that even by the slightest amount, it will laze, it will have positive gain, right. So, in order to find this out, I need to equate g. So, the answer is, okay, I will find out by equating g to unity. Let us do that and find it out. So, I will keep this part. So, my g is, I am equating g to the unity. So, what I can write is R1 R2 multiplied by this exponential term equals to 1, right. So, what I can do is equals to, if I take logarithm e based, so log e 1 by R1 R2, all right. Now, what is this x actually? We have been writing about the distance. This x is essentially my cavity length for a round trip, okay. So, this length is L, right, we have learned this in last few classes. So, one round trip means is going and coming back, which means x is essentially 2L. If you look at this expression where we introduce this R1 in R2, it should tell you clearly that we are considering a round trip, okay. Without a round trip, I cannot, complete one wavelength even, okay. So, for that we are having this x equals to 2L. So, what I will do, I will get into 2L equals to this quantity, right. So, what do I need to find out? I need to find out this k, okay. So, my k is equal to gamma plus 1 upon twice L okay. Now, this k is a special key. Why? Because we obtained it by putting this threshold condition, that is g equals to 1. Okay. So, this actually led to this k value, right. So, I will specifically mention this one as k threshold, all right. Now, what do I need to do so that I get finally a laser output? What I need to do is to do something so that this K, which is my small signal gain coefficient, should be greater than this one, right. So, what I need to have here is into minus G2 by G1 C prime should be greater than this. Okay. So, this is the condition for achieving laser amplification. Okay. So, this is for actually getting laser output, a true laser output. If I have this value, that is the gain coefficient, less than or equal to this threshold value, I will not see any laser output. Only it goes above this value, I get a laser output. Okay. So, this is how we get the condition for getting laser, okay, the threshold condition for getting laser. So, today we will stop here, and in the next class we will look at certain properties of laser which you have already heard of. We will see what are the basic reason for having those properties, say for example directionalities, or a beam diameter, beam width, coherence and monochromaticity, intensity, etc., etc. And we will also relate certain applications to these properties. So, we will see you again in the next class. Thank you very much.